Awesome. Thanks so much for the introduction. Hi, everybody. My name is William Key. I'm a scientist in the autonomy behavior group at Latitude AI, and also a previous member of the prediction team at Argo AI. So our fearless leader, James Hayes, unfortunately couldn't make it to CVPR this year, and Andrew's flight is currently delayed. So I have the privilege of being your MC for the competitions today. And before I begin, I wanted to extend a quick thank you to the workshop organizers. The Argoverse team has attended some form of this workshop for the last few years, and it's hard to overstate how drastically the data, challenges, and approaches have changed, even in a few short years. So these workshops are important community checkpoints, and they have huge influence over the next 6 to 12 months of work. So a big thank you to those who put this together, submitted papers, and participated in these competitions, and especially to those who have been a thread of continuity over the last few years. So for our talk today, I'm going to give a quick overview of Argoverse, present our motion forecasting challenge, and then hand it off to 3 excellent PhD candidates. Tarasha, Nihar, and Nate will present our other challenges. So the high-level teaser here is that this year we ran 4 competitions across perception and prediction, and all of them were new for Argoverse. 2 of these competitions were on established tasks. In this case, it was multi-agent motion forecasting and end-to-end forecasting. And 2 of these were actually pilot competitions in the form of self-supervised scene flow and 4D occupancy prediction. All of these challenge leaderboards will remain up, and we encourage you to continue benchmarking new methods using Eval AI. So before we dive into the competitions, I wanted to give a quick overview of the AV2 datasets. For those of you who are familiar with Argoverse, and especially AV2, thank you for being a part of our community. And for those of you who have yet to try Argoverse, we'd love for you to download it and give it a spin after today. So a little bit about AV2. Last year, we released a set of rich and complex data sets with a focus on usability. All of the data in these data sets were collected from a fleet of vehicles equipped with 2 360-degree long-range LiDARs, 7 HD cameras capturing 360-degree imagery at 20 Hertz, and 2 forward-facing stereo cameras. These source logs were collected in 6 US cities with varying weather, infrastructure, driving conventions, and actor behaviors. So these cities were Miami, Austin, Washington, DC, Palo Alto, Pittsburgh, and Detroit. So all the cities that Argo AI used to operate in the US. And these logs also contain both raster and vector maps, as well as precise map-aligned pose. So the first data set I'll cover here is the sensor data set. The development of this data set was led by Ben Wilson, and it was designed as a benchmark for 3D detection, multi-agent tracking, and even end-to-end forecasting methods. So this data set consists of 1,000 scenes. Each of them is 15 seconds long with HD map data, along with high-quality human annotations in the form of amodal cuboids and object types. And because of where the logs were collected, the scenes are both dense and diverse. We made a concerted effort to support a large number of different object classes. In our case, it numbers 30 in all. We also chose to include tracks at range, as early detection and tracking of these vehicles is important for maneuvers such as unprotected lefts. And just a quick note here before we continue on. In all data sets with imagery, we blur faces and license plates to protect privacy. And for Argoverse 2, we also released a large unlabeled LiDAR dataset. The intention here was to support the continued development and improvement of self-supervised methods. And each of the 20,000 30-second scenarios we have was mined from Fleet, with a focus on interesting behavior. We define interesting using a superposition of scores for kinematic, map structure, and social relevance. And next, we have the motion forecasting dataset, which is large in terms of scenarios, but very small in terms of storage consumption. By cutting out sensor data, we're able to provide a lot more scenarios containing only track data and semantic vector maps. So this makes this dataset a great resource for developing object-centric forecasting methods. And unlike the previous iteration, AV2 scenarios are now 11 seconds long with up to 10 different object classes. Scenarios were again mined for kinematic, map, and social relevance, and we see a strong positive correlation between a scenario's interestingness score and the difficulty of forecasting key actors in that scenario. Finally, AV2 has a unique map change dataset that was developed by John Lambert and published under their paper titled Trust But Verify. This dataset aims to tackle the very real operational challenge of identifying when HD maps used by autonomous vehicles have changed. These changes could result from something as simple as a refresh of lane lines or real structural changes to the underlying road connectivity, which could occur after construction. So this dataset again includes all LiDAR imagery and comes in at just under 1 terabyte. Pre-trained models and training code are available and are linked in the user guide, which I'll talk about next. So with so much data available across various modalities, we wanted to make it as easy as possible for anyone to download scenarios and get started. So to support this goal, Ben has built out a new user guide, which you can find by following the link above or by scanning the QR code here. The user guide includes a more complete description of all the data sets we've talked about today, as well as installation instructions, schema outlines, and really everything you might need to get started with Argoverse. And finally, as many of you may know, Argo AI closed in November of 2022. So what does this mean for the future of the Argoverse project? So a little bit of history. Argo AI was founded in late 2016 and focused on L4 urban driving for delivery of people and goods. The company deployed in multiple cities across the US and Europe and partnered with 2 major OEMs. And it was during this development effort that all the logs were collected for the AV2 datasets. And over time, these datasets have become important assets to the research community, guiding and enabling research to solve real-world safety-critical problems. So for this reason, we are immensely grateful to Argo and its partners for protecting this project and its history. By transitioning stewardship to James Hayes at Georgia Tech, and this group of collaborators spread across academia and industry, our efforts will continue. So Argoverse will continue to serve as a source data for new challenges and competitions. And more than ever, this is now a community effort. So if you would like to be involved, please come see us or feel free to reach out at any time. So now on to this year's motion forecasting challenge. I'll start by motivating the new multi-world problem setup, present this year's results, summarize some trends we've seen, and then wrap up with some directions for future work. So again, revisiting history. The motion forecasting challenge is now in its 5th year running. It's run continuously all the way since the first iteration back at NeurIPS 2019. And in every iteration, we've incentivized the community to think about the problem in different ways by varying the evaluation metrics and problem setups used. And over the years, these challenges have proven popular with the community, with a flurry of sequential work quickly saturating performance on the original Argoverse 1 dataset. So to keep the community moving forward, we released the AV2 dataset last year, which introduced 250,000 new forecasting scenarios collected in 6 cities spread across the US. And at the time of release, this is geographically the largest forecasting dataset that had ever been released to the public. And this dataset isn't just large in scale. Scenarios were specifically selected to be both challenging and interesting from an autonomous driving perspective. Combing through thousands of hours of real-world logs, we mined for scenarios where actors interacted with the AV. We also searched for dense, socially complex environments and looked for situations where non-vehicle actors were present. And in the first challenge we hosted with this new dataset, we used a single agent forecasting setup centered around a focal agent. However, planning safely in the real world requires us to understand the intentions of more than just one actor in the scene. So looking at the scenario on the right here, we can see that there are multiple nearby actors that are relevant to the AV's decision-making. So this necessitates multi-agent forecasting. But if we naively generate disjoint predictions for each actor, this puts significant burden on the downstream planning system. And even for humans looking at figures like the one on the right, it can be really difficult to disentangle the individual features and figure out what's likely to happen next. So to address this problem, we embrace joint prediction through the concept of worlds. Instead of generating sets of predictions for each individual actor that could be disjoint, methods must instead generate predicted worlds, which capture how the future state for all actors in a scene will jointly evolve. And to understand the relative likelihood of each world, we also require submissions to generate an accompanying set of normalized probabilities. So if you visualize a set of output predictions, it might look something like what we have in the video here. And more concretely, the problem setup is to use inputs in the form of actor histories and static map features to generate outputs in the form of worlds. Each world must jointly capture future states for all actors along with the likelihood of that future materializing. To ensure that we only evaluate over actors that are relevant for planning, we mark a subset of them as scored actors and summarize results over only that set. So how do we measure the quality of multi-world predictions? Let's start with a quick refresher of metrics from the single agent setup, with min FDE measuring the distance between the best prediction and the ground truth at the final time step. The miss rate captures the proportion of actors with min FDEs greater than 2 meters, which we consider to have missed. And finally, we have Breyer min FDE, which adds a probability-based penalty term to incentivize predictions to be confidently accurate. So if you take a look at these metrics from a multi-world perspective, each of these metrics can be translated to a world-based equivalent. And starting with the FDE, we report the min world FDE as the lowest mean FDE out of all predicted worlds, summarized across the scored actors in each scenario. And using the same setup, we can convert Breyer FDE to min world Breyer FDE. The final metric we report here is the actor miss rate, which reports the proportion of scored actors that missed in the world with the lowest mean FDE. We refer to that world as the best world. So now that we've taken a look at the metrics, let's take a look at this year's challenge results. So despite the short time frame, we received more than 100 submissions from 15 teams this year, including participants and prize winners from multiple previous iterations of this challenge. So it's always super exciting to see continued progress in the community, especially with teams returning year after year and iterating on their previous methods. And this year, we'd like to congratulate the QCNet team for winning the 2023 Argoverse Forecasting Challenge. This team is made up of Zikang Zhao, Jianping Wang, Yanghui Li, and Yukai Huang. They'll also be presenting during Thursday's poster session later this week, so please drop by if you'd like to learn more about their work. And if we take a closer look at the leaderboard, the results are especially notable as we can see a big gap in performance between our challenge winner, QCNet, and the runners-up. In each metric reported, QCNet posts a greater than 30% distance to the next best method, which is forecast MAE. The third place finisher, History Info, posts an actor miss rate that's almost twice as high. So the results we're seeing from QCNet are seriously impressive. And what's even more exciting to see is that when we look at cross leaderboard results, QCNet places first on every single Argoverse forecasting setup to date. And even compared to last year's AV2 challenge winner, which we show here on the left, QCNet posts significant improvements across the board. If we take a look at the AV1 leaderboard, percentage improvements are a bit smaller, as the metrics improvement have largely plateaued over the years, but it's still very encouraging to see continued progress on the older data set, and very impressive to see a single method on top of all three leaderboards. So what sets QCNet apart from the other approaches? At a high level, their method involves encoding information in local coordinate systems with spatial temporal positional embeddings. These features are then fed into a factorized attention-based encoder for both actors and map elements. And by encoding all positional information in local coordinate frames, the encoder is able to reuse embeddings without renormalizing across time steps. This allows for more efficient forecasting in a streaming setting. Finally, the learned embeddings are used as inputs for a two-stage Dieter-like decoder, which first generates anchor-free joint proposals before refining into predicted trajectories. So let's take a look at the encoder itself. And we can see that QCNet uses factorized attention with queries attending to key value elements along one axis at a time. So in this case, the axes are temporal attention, followed by agent map attention, and then social attention, which is another name for agent-agent attention. So by not squeezing the time dimension first, QCNet is able to fuse information at every time step in history, instead of only once at the end of the observation window. However, if you were to run factorized attention naively in a streaming setting, it can get really, really expensive, as inputs must be renormalized as new coordinate frames come in. But by encoding in relative coordinates, QCNet sidesteps this issue, as map and actor embeddings can be cached and reused as new data arrives. So this shaves off a computational factor of T from the complexity of follow-up forecasts, which has important real-world implications and makes it much easier to deploy on a real-world autonomous vehicle. And next, if we take a look at the decoder, QCNet adopts a two-stage Dieter-like architecture. So we have learned anchor-free mode queries which are used to generate joint trajectory proposals for all scored actors in each world. These trajectory proposals are then used as anchor-based mode queries in a refinement module. They use row-wise attention to capture relationships between actors and column-wise attention to ensure diversity across worlds. So each of these modes and worlds will specialize in something different. As a last step, the output embeddings are passed through an MLP to obtain final world trajectories, as well as the associated probabilities. So QCNet definitely makes some interesting contributions, but I think most of us are visual people. So let's take a look at some qualitative results that highlight the method's strengths. In this set of visualizations, you can see that QCNet does a much better job reasoning about social relationships, as well as map affordances when compared with history info, which was the third place finisher. We can see that while history info generates a set of predictions that includes multiple collisions, QCNet learns that perpendicular vehicles at intersections generally don't start moving at the same time. It also learns that vehicles, when making left turns, generally end in unoccupied travel lanes, while the other method is a little bit more scattershot with its predictions, sending at least one of its trajectories into a parked car. So if we take a look at a different example from a pedestrian crosswalk, we can see that QCNet again does a better job reasoning about social relationships. In this case, QCNet generates collision-free vehicle trajectories that only accelerate after the pedestrians have cleared the intersection. While we can see that history info again generates several worlds that contain overlapping collisions. Okay, so we've seen a few examples where state-of-the-art methods today do great, but some types of scenarios remain difficult for even the best methods to solve. And if we take a look at predictions from QCNet, we can see that it still struggles with scenarios that include complex map geometry, such as scenarios that might be encountered at roundabouts. Scenarios with complex map topology, like 5- or 6-way intersections, can also be problematic, because in these situations, models often struggle to capture the full range of viable outlets. And when you have 5 or 6 different ways that you can head, the number of viable outlets can quickly reach double digits in complicated settings. And another class of scenarios that even the best methods still struggle with is lane changes. So whether actors are making wide turns, overtaking slow-moving vehicles, or simply shifting left to right on a travel lane, there can be a huge range of high-level actions to cover, as well as variations within them. So when you only get a handful of guesses for how the future is going to evolve, diversity matters a lot, and each prediction counts. It's possible that in some situations, 6 worlds just isn't enough to cover the full range of relevant futures. And finally, we have U-turns, which can be difficult to reason about even for humans. So when vehicles make a U-turn from a stop at an intersection, it can often be really hard to distinguish between what's going to be a left turn and what's going to end up as a U-turn. Sometimes it's not clear even to humans until the actor is halfway through the maneuver. And another reason why it can often be difficult to predict in these situations is that U-turns are generally low probability and usually aren't associated with a specific lane segment. So this makes it extremely hard to capture this kind of behavior using standard map attention-based frameworks. Further progress in this area may require additional data augmentation or integration of historical data from external sources. So if we understood the overall likelihood of someone making a U-turn at a specific intersection, that might be useful information to integrate into a model. And wrapping up today's discussion, I'd like to revisit some of the trends we've seen in forecasting over the last few years, and discuss a bit about where we think the community might be headed next. So one of the first big trends we saw was the use of vectorized inputs. And this was first popularized by methods like LaneGCN and proven out on Argoverse 1. Afterwards came the proliferation of multi-stage architectures with 2-stage decoders. This was proven by methods such as LaneRCNN, TNT, as well as previous challenge winners on the AV2 single agent setup. So we saw a lot of these methods do really well last year. And more recently, this year, we've seen an increase in methods focused on viewpoint invariant encoding and fast inference. So this includes methods like GoRela and QCNet. And this sets the stage nicely for future work on streaming forecasting, which brings the research setting closer to how forecasting models are actually used in the real world. So future competitions could task methods with continuous prediction of new trajectories, which would require efficient fusion of new information coming in, as well as careful exclusion of irrelevant history from the past. Another problem with real-world relevance is forecasting under bounded compute, where methods could be tasked with generating the best set of predictions given a dynamic compute budget. So we'd love to explore these problems in future Argoverse challenges. And finally, to direct the community's focus to specific hard problems that remain, we'd love to create targeted test sets for difficult behaviors such as lane changes. And to support research in this area, we could either try to curate data from the existing data sets or compose new scenarios released in an AV2 format. And we hope that by giving the community the tools and data to tackle these problems, next year's advancements will be even more exciting than the last. And that wraps up this year's forecasting update. Thank you all for listening. We hope you'll be back next year to see what comes next.
Thanks, Will. So my name is Nihar, and today I'm going to be talking about end-to-end forecasting. So end-to-end forecasting is really motivated by an observation that there are two almost sub-communities within perception research. We have the detection and tracking folks, where they assume you have noisy sensor inputs and noisy intermediate representations, and their algorithms really need to account for this. And on the other hand, we have the standard motion forecasting challenge, which assumes ground truth tracks as input. However, in a real self-driving scenario, it's important to reason about the sort of the noisiness in tracks and potential issues that you may have at each stage in the pipeline. So through this end-to-end forecasting challenge, we aim to build a unified setup where we can explore all angles of perception. So in this talk, I'm going to assume that everyone here is probably an expert in maybe 1/3 of all of these challenges. So I'll go through some of the details and relevant metrics for each. So for this year's inaugural challenge, we had 10 teams compete, and we had over 200 leaderboard submissions. And we had 3 sub-challenges. So although end-to-end forecasting is really about taking sensor input and producing each of the individual components of the perception stack, we break down and evaluate teams on detection, tracking, and forecasting. So first, let's talk about the first sub-challenge, which is 3D object detection. Now, the setup here is exactly the same as last year's 3D detection challenge, where we had a 150 by 150 meter range in which contestants are supposed to detect objects. We have a long tail ontology of 26 different classes, and all competitors have access to LiDAR point clouds and RGB images. So the primary metric by which we score different algorithms is the composite detection score. Quickly, I want to go through an example of evaluating car CDS. So here we have 3 ground truth boxes, and every model will create some predictions, and each prediction has a confidence score. So these are shown in blue. Now, the predictions that overlap the ground truth, which is defined by some center distance, we call these true positives. And for these set of true positives, we can compute some auxiliary metrics like average translation error, average scale error, and average orientation error. So now remember, this is all very much inspired by the new scenes detection challenge, which does something very similar. Predictions that don't overlap any ground truth, well, these are false positives. And ground truth objects that have no match predictions, these are considered false negatives. So with all of these different ways in which we can factorize our model predictions, we can compute average precision by basically drawing out a precision recall curve and taking the sum of the area underneath the curve as average precision. And for the set of true positives, we can compute normalized translation error, scale error, and orientation error. And CDS is just a product of average precision and a sum of these normalized true positive errors. So for this year's challenge, we had Team LE 3D E2E as our winner. And we'll be seeing this team a lot throughout this talk and for all the other challenges, because they've taken a unified approach, meaning that they have a single model trained end-to-end to solve all three sub-challenges here. And the way in which their detector component of their method works is they take a LiDAR point cloud and code it with a second backbone to generate some LiDAR bird's eye view features. And they take RGB images from our 6 ring cameras and pass this through BEV-former to generate RGB BEV features. They perform spatial fusion, much like BEV fusion, from MIT. And they performed this over different time steps to generate a temporal sequence of RGB LiDAR features. Now, these features are then fused to generate a single temporal feature. Now, the single temporal feature is passed into a deformable deader head. And this is how this model produces 3D bounding boxes. So importantly, this team ensembles 8 different models with respect to different voxel sizes, different resampling strategies to deal with common classes and rare classes, and train some models with multimodal input and some models with just LiDAR only input. And they fuse all these different ensembles using weighted box fusion. So we can compare this model directly to last year's winner, which is from Team Detectors. Now, this team used a LiDAR-only ensemble of different center point models and was able to get 34 CDS. And in contrast, this year's winning team was able to significantly improve this to 39 CDS. And this improvement is mostly due to improvements in how they fuse multimodal input. So we can break down the performance and compare last year's winner with this year's winner across range. So importantly, in the 0 to 50 meter range, this year's winner improves by about 5%. In the 50 to 100 meter range, this year's winner improves by about 6%. However, in the 100 to 150 meter range, they're only able to improve by about 2%. This really suggests that the challenge that remains in Argoverse is in long range detection. So we need to think of creative ways of tackling this long range detection problem as a community. We can also break down performance by rare categories and note that we see significant improvements on strollers, wheelchairs, and dogs. For example, this year's winner is able to improve stroller performance by almost 20%, wheelchair performance by more than 25%, and nearly double performance on detecting dogs. And this is really, again, because multimodal cues significantly improve rare class detection. And this is because it's difficult to identify these objects from sparse LiDAR alone. So having this RGB signal is critical. All right, so that's our first sub-challenge, and now we'll move on to the second sub-challenge, which is 3D multi-object tracking. Now, the problem setup here is a little bit different. Here, we're only interested in looking at a 50 meter by 50 meter range, because as we mentioned, long range detection is still an open problem, and I think it's important to scope this problem appropriately. So before we go to long range tracking, let's first make sure we can solve this near range tracking for long tail classes. Here we still require the teams to detect 26 categories, and they have the same inputs. But importantly, teams can also take as input either predicted detections or start from the raw sensor data. Now, the metric we use here is a higher order tracking accuracy, or HOTA, and this is a popular metric which has been adopted by the Kitty dataset, the Kitty tracking challenge, so we decided to adopt it as well. And importantly, this metric decomposes tracking into 3 parts, namely detection, association, and localization. So in order to do well on this HOTA metric, it's not enough just to have a good detector. It's not enough just to have a good association algorithm. You need to do well on both of these components. And the winner of this challenge is, again, Team LE3D-E2E. And the way in which they approach this challenge is by creating a multitask head. So recall, they process RGB and LiDAR features to generate this single temporal feature. The single temporal feature is passed through deformable deader, and they use the detection queries from deformable deader to initialize the tracks for MOTAR. And they simply use this off-the-shelf method, and they find that this works quite well. And the second, the honorable mention for this challenge goes to Team AutoDrive. They take a slightly different approach, following a more standard tracking by detection paradigm. And they're able to improve over our tracking by detection baseline by improving the NMS to improve the detections coming from their center point model by considering IOU and classification scores. And we can compare these two model performances, and we see that the end-to-end approach performs almost 10% better than the tracking by detection approach. And we attribute the majority of this performance difference due to the difference in the quality of detections. So importantly, Team AutoDrive only uses a LiDAR-only detector versus Team LE3D-E2E uses a multimodal detector. And we can also break down performance across categories, and we see the same trends continue. with better detections, we're able to do better at tracking rare categories like wheelchairs and wheeled devices. So think stroller, skateboards and scooters. And we see an almost 40% improvement for wheelchairs and a 30% improvement for wheeled devices. All right, now we'll move on to the last of the 3 sub-challenges, which is end-to-end forecasting. Now, the problem setup here is very similar to the tracking setup, where we look at a 50 by 50 meter range. We ask teams to evaluate forecasting performance on 26 categories. And importantly, teams can choose to either use raw sensor data or predicted tracks. And we choose a sliding window type approach. So for this challenge, we use the Argoverse 2 sensor data set, which has 15-second logs. And we allow teams to use an unbounded history, but ask them to forecast 3 seconds into the future. And we can repurpose the sensor data set for forecasting by simply sequestering parts of the ground truth tracks. So the metric we use here is a new metric which we introduce called forecasting AP. And I want everyone to recall how we compute true positives for detection. So true positives in detection just requires that you have sufficient overlap in the current time step. We simply extend this metric by also requiring that predictions must overlap the ground truth in both the current time step and the final time step. And once you compute this, you can use your AP computation toolkit and get this metric as usual. Importantly, we evaluate different subcategories. So we bucket each ground truth and predicted trajectory into either static, linear, or nonlinear buckets. And we use a sort of heuristic to determine these buckets. So a ground truth track or a ground truth forecast is static if the final position is well approximated by no motion. It's linear if it's well approximated by constant velocity, and everything else we consider to be nonlinear trajectories. And importantly, we have a very long tail distribution of trajectory types. So most of the things you see in the world are static. So think parked cars. And many of the other cases we see are things moving in a linear fashion. And the rare examples here are the nonlinear examples of motion trajectories. But it's important that we do well on all 3 of these categories. So we compute metrics for each of these subcategories individually and weight them equally to get our average MAP. And the winner here is, again, team LE3D E2E. And they take a multitask approach, just as they did for tracking, by taking their temporal features, feeding them through deformable data to get their detection queries. And they take HD maps, pass them through VectorNet to generate map queries. And they concatenate both of these into Motion Former, which is a submodule of UniADE, which is an award candidate here at CVPR'23. And they use this to produce their predictions. And an honorable mention here goes to team DGIST CV Lab. And this team takes a very different approach. So they use a simple LSTM module and take a stage-wise approach where their input is predicted tracks coming from a center point detector and gradient association algorithm. So their input features here are the position, velocity, and angles of all the trajectories. And they directly predict forecasts for 3 seconds into the future. So they make 3 very interesting observations here. So very similar to the winner of the standard motion forecasting challenge, this team also uses an object-wise coordinate frame. So they reframe everything into this object-wise coordinate frame. But importantly, they spend a lot of time designing different data augmentation strategies. So one strategy they use here is they jitter the ground truth trajectories based on the speed and velocity of each of these objects, and they're able to generate much more data that way. And they also impute some noise into their ground truth trajectories by masking out some of these points, and they replace it with some linearly interpolated pseudo trajectory. And they find that these data augmentation strategies are incredibly useful. And we find that the end-to-end approach, which is LE3D E2E, and the stage-wise approach are very close in terms of forecasting MAP, where the end-to-end approach beats out the stage-wise approach by just 1%. So this really suggests that there's still room for exploration here to determine if the right way to go is a stage-wise approach or if we should really be investing into this end-to-end paradigm. So we see that both methods perform quite poorly on nonlinear movers. And again, this is because nonlinear movers represent such a small fraction, and detecting and forecasting these rare objects is quite difficult. So there are many future directions for end-to-end forecasting, and I want to highlight 4 things. So again, as we mentioned, this paradigm of end-to-end versus stage-wise methods is something that's worthy of future exploration. I think limiting ourselves to just the sensor data set may not be the right answer, particularly since there are so few examples of interesting scenarios in the sensor data set. So one thought might be that we want to leverage trajectory level motion forecasting data and use that to improve our end-to-end approaches. There's also a lot of room for exploration of multimodal fusion for long-range perception, particularly because we see that even the best multimodal approaches are still unable to perform very well at long range. And finally, we saw a lot of methods that used ensembles in this year's challenge, but this is infeasible when we want to run these things on car. So taking runtime into account will be critical for adopting these into a real self-driving vehicle. And with that, I'd like to thank everyone for their time and pass it off to Tarasha.
Hey, everybody. I'm Tarasha, and I'm a PhD student at Carnegie Mellon University. So we just looked at 2 of our challenges on established tasks, and now Nate and I are going to talk about 2 pilot Argoverse challenges that we hosted the CVPR for the first time. So let me start with the one on 4D occupancy forecasting. And actually, before we jump into the challenge setup, let's take a moment to pause and understand why we are talking about forecasting what is being called the 4D occupancy of the world. So recall that for perception and prediction tasks that we saw till now, lots of costly human annotation is needed in the form of object tracks, labels, bounding boxes, and HD maps of cities. But this annotation process is without a doubt not scalable. So we want to encourage tasks and methods that do not completely rely on these annotations, but are rather self-supervised so that they can take advantage of terabytes and petabytes of data being collected by fleets every day. And one such task in the autonomous driving world is called point cloud forecasting. So given a set of past LiDAR sweeps, it aims at predicting the future LiDAR sweeps. And no annotations are needed for this task because the ground truth LiDAR sweeps are already available in the future logs. Now, while this may seem straightforward, understanding where every point in a point cloud is going to move in the future is non-trivial. And that is because points depend on the intersection of rays from the LiDAR sensor and the environment. And these rays change with the moving ego vehicle, and they change with the ray sampling pattern in every LiDAR sweep. So then accurately forecasting points requires accurately forecasting extrinsics, intrinsics, and the motion of the environment. So we argue that from an autonomy standpoint, it only makes sense for autonomous systems to make predictions about the environment that they are in and not the calibrated LiDAR sensors that they are equipped with. And to this end, instead of directly learning to forecast points, we propose that methods instead learn and forecast the underlying spatiotemporal or 4D occupancy of the world. And once we have this occupancy, we can easily render it into future point clouds. So this brings us to a problem setup where we learn a more useful and generic quantity from exactly the same training data as point cloud forecasting, and once again, without any annotations. And we call this setup 4D occupancy forecasting. All right, but then how does one even evaluate occupancy? Because of course, we don't have access to ground truth occupancy, which would have been the gold standard. But we do have point clouds that can be rendered from this occupancy. So for evaluation, we give methods query rays, along which they have to predict the distance that the ray travels before hitting a surface. And based on this distance, we calculate the L1 and absolute relative errors as our primary evaluation metrics. Okay, so now we know the task and the benchmarking protocol, so we can get back to the challenge setup. So for this challenge, we allowed methods to look at the past 3 seconds of data, and we asked them for forecasts for the next 3 seconds. And we defined a bounded volume, which we called the near field volume. And this was the region inside which we computed all the metrics. So traditionally, there's also chamfer distance that is used for evaluating point cloud forecasting. So we compute that inside the near field and also using the unbounded point cloud. So out of 12 entries that we received in our pilot competition, the winner was again team LE3D E2E. And if we compare their entry with the 2 baselines, which was ray tracing and 4D occupancy, the baselines that we provided for the task, LE3D E2E had an 18% relative performance improvement over the baselines. And just to be clear about what each method does, I want to point out that the ray tracing baseline is non-learned. So it just aggregates point clouds from the past and assumes a static world. And then the 4D occupancy forecasting baseline, which is appearing at the CVPR, it roughly initializes a 4D voxel grid from the past point clouds and passes this through a unit kind of architecture and gets a 4D voxel grid of the future. And where the winner really shines in comparison to this is that their initial voxel grid is an output of Ocformer that operates on temporally fused bird's eye view feature maps using cross-attention layers. So it's really the initialization of the 4D voxel grid from the past that makes the winner shine. And now just a reminder that both the methods actually learn a 4D occupancy as an intermediate representation. And this we claim is more generic and applicable. We are not going to be able to see the occupancy in the qualitative results next, but these are available as part of these methods. And just a shameless plug, but if you want to learn more about why and how we try to do this and what all applications the occupancy can be used for, you should visit our poster on Tuesday morning. Okay, so let's look at what these methods look like in action. And starting with some successful cases for the winner, we see here that in the case where the environment is mostly static, all methods do well, but LE3D E2E actually gives sharp object boundaries. And then also for very thin structures that are static, it is able to reconstruct them in the future, while the other baselines struggle with that. And then when forecasting dynamic objects, LE3D E2E tries to predict moving occupancy, but for the baselines, either these dynamic objects are always assumed to be static, or they incorrectly diffuse over time and change shape over time. And then some cases where all the methods fail happen when the moving objects are completely omitted from the forecasts, or they suddenly cease to exist in the future, or the ego vehicle ends up colliding or passing over the objects. For example, what is happening here with the ray tracing baseline. Okay, the other failure cases when objects that have very few LiDAR returns on them, when these objects are dynamic and moving, for example, pedestrians, which is a really important semantic class, they are never learned to forecast properly. So naturally, these failures open lots of avenues for improvement in the future. And we hope the challenge, which by the way, will remain open even after CVPR, we hope it will encourage more creative methods for 4D occupancy forecasting, maybe by time forecasting with downstream applications like motion planning, or by resorting to multi-hypothesis forecasts for dynamic objects and dynamic scenes. Thank you.
Hi, everybody. I'm Nate. I know we're running a little bit over time, but I promise I will be brief and get everybody off lunch. So I'm going to be presenting on our second pilot contest on self-supervised scene flow. So what I'm showing here is two LiDAR scans. One is of a car and one is of a tree and is lagging. And so I think we can start with sort of just a rhetorical question, which is, why do we have a semantic class and care about detecting cars? And do we not have a class and don't really care about detecting trees? And maybe you'd say it's like, okay, well, trees aren't in the middle of the road usually, but I think the clear answer is that cars move and trees don't. Out of the 30 Argoverse classes, 26 of them are dynamic moving objects. And that's just a reflection of the fact that anything that moves needs to be tracked. And so traditionally, of course, you do that at the object level. But SceneFlow is another view of this problem where instead of doing it semantically, we look for low-level motion cues. So what is SceneFlow? Sort of the classic computer vision answer would be that it's the 3D analog of optical flow. It's the motion of all points in a scene in 3 dimensions. But in autonomous driving specifically, generally what we are interested in is the motion of all points in one LiDAR scan between one frame and the next. So here is a car in one frame. Here would be, a 1/10 of a second later, the same car. And so just the goal of the problem is to produce a dense set of flow vectors like this that shows you where everything is moving. And sort of what's interesting about this problem that sort of changes it from the detection and tracking view is that, like classic optical flow, this problem can be solved without labels. Now, while we hopefully don't need any labels to estimate our scene flow, we do need them to evaluate competition results. So how do we get those? Now, annotating all of the 50,000 points in the scene would be incredibly time consuming and difficult. So instead of that, we rely on the object labels, which we already have and are much easier to get. In each frame, we have corresponding bounding boxes from one to the next of how every object moves. So given those boxes, we can extract just the rigid motion parameters that relates the two. And then once we have those, we can apply the transformation to every point to get out individual motion vectors. Okay, so then once we have our ground truth flows and we have some self-supervised method that predicts them, we need to evaluate. The traditional metric for both optical flow and scene flow is endpoint error, which is just the norm of the difference between the ground truth and the prediction. But just using that directly is a big issue for the autonomous driving case, because when you're working with these LiDAR point clouds, the vast majority of the points belong to the background. And so if you just took the average over everything, really all you're measuring is your ability to predict that the ground isn't moving, which isn't very interesting. So instead of doing that, we use a 3-way average across 3 classes of points. The first class is what we call dynamic foreground points. Those are any points that we have determined from the labels are moving faster than 0.5 meters per second. The second class is also foreground points, but ones that are currently not moving. And then finally, we have all of the backgrounds separately. So then we just take the unweighted average of these 3 point-wise endpoint errors to produce our final metric. So we have our data, we have our evaluation metric, and so we start with just seeing where are we currently? How do current methods perform? So we evaluated a set of 5 recent methods that are either self or even just weakly supervised. And we found in general that the performance actually isn't that great. The purple bars are the completely self-supervised methods. The blue bars or green are the weakly supervised methods. And then here in orange is the performance of a method that is completely dataless. It's just a test time optimization that does every example from scratch. It's called neural scene flow prior. And you can see that it almost gets the best performance out of all of these methods, even though it doesn't use any learning. And this was really one of the main motivations we had for running this competition, that there are clearly lots and lots of gains available for learning methods, even self-supervised learning methods, to succeed, since currently they are not even performing as well as something that doesn't use any learning at all. So unfortunately, I guess since this was a new contest, we didn't get a ton of submissions and nobody actually beat neural scene flow prior, a baseline. So to close out, I'm just going to quickly explain that method from a high level, and then explain our best novel submission. So like I said, neural scene flow prior is a test time optimization method, and it's based on the use of coordinate networks. So what that means is for each scene, they just take a fresh MLP that takes as input just 3-dimensional XYZ coordinates, and the network needs to output the flow at that position. And they optimize that for each scene by essentially, taking all of their points, putting them through the network to get all their flows, deforming the first point cloud to the second frame using those predicted flows, and then minimizing the distance between those 2 point clouds. And to measure the distance between those two, because there are no known correspondences and actually no correspondences at all in general, they use what's called the chamfer distance, which is like a symmetric version of the nearest neighbor distance. Basically, it does nearest neighbors both ways. There are a little bit more details for the full thing to make it work, but that's the high level idea. Okay, so our winner really and best new submission is the zero flow work from Kyle Vetter. That method takes a sort of a distillation or a student teacher approach, where first they run the neural scene flow prior optimization over the entire training data set of Argoverse to get a set of pseudo labels. And then they take a very fast feed forward network and train it in normal supervised fashion just on the output of neural scene flow prior, basically. And so this manages to achieve basically the same endpoint error as neural scene flow prior, but it's, I think, 2 orders of magnitude faster, since they don't need to do any optimization. And so now we'll just close out with some qualitative looks at the predictions. So this is an output from zero flow on sort of like the best case for basically any method, which is a dense, reasonably fast moving object that's close to the vehicle. So this is a car that's very close by, and you can see we get tons and tons of returns, and that's quite good. A slightly harder case is just when we move a little bit further away from the vehicle. So this is outside of the 35-meter range that in our sort of more broken down evaluation on the leaderboard we call the close range. And you can see that we get far fewer points. And on the right, the predictions as opposed to the ground truth are missing a lot of predictions on them. And average over the whole data set, the endpoint error almost doubles when you go outside this 35-meter range. And finally, probably one of the hardest but most important cases is pedestrians, since they're both small, so you don't get very many points, and they don't move very fast. So this is a person, maybe a little hard to see, this is a person walking next to a pickup truck. And so you can see that there is motion in the ground truth flows on the left, but there's just nothing being picked up at all by the predictions on the right. So this, basically none of the methods we tested do well in pedestrians at all. So this is definitely an area for future research. So there's a lot to be done. So that is all I have on this contest. We will be running in the future, and the leaderboards will stay online. So I hope people continue to submit. We want to thank everybody for submitting to all of the contests. All of the reports on all of the submissions are available if you want to go through them. And for the winners, if you would like to pick up your certificate, you should find Nihar after lunch, and he has them for everybody. I think that's everything. We're probably out of time for questions, so I just say thank you again.